Good morning, everyone. My name is Mohammed Barhdadi, and I am a Master's 2 student. And actually, I'm in internship for 6 months in a Carter laboratory in Technolac based in France. And today I will present you my research project about sensitivity of lacustrine carbon burial rates to first human activity during the Holocene. And we see the limits and opportunities of meta-analysis in paleolimnology. So to start, we know that the terrestrial ecosystems and ocean store a large amount of carbon that we see in the figure compared to the amount stored by lake. But if we take into account this amount stored by lake in a large time scale, for example, the Holocene, this amount will be very important and will be very significant. And that's why I choose the lacustrine carbon for my study. So the source of this carbon may be autochthonous by primary production or allochthonous by watershed input. And it represents the fraction of organic matter which will be permanently buried in sediment and which is not recycled in ecosystem. There are many variables that could control this sequestration, and we have some temporal variables like precipitation, landscape, temperature, and primary production. And we have some special variables that, for example, in literature, it has been shown that a lake with a small surface area could store a large amount of carbon than lake with a large surface area. And the same thing with a watershed. It has been shown that a watershed with a large surface area allows the lake to store a large amount of carbon. So our scientific questions are, how does the carbon sequestration vary during the Holocene? And is the meta-analysis approach appropriate to reconstruct the trajectory of carbon sequestration and primary production? And what are the factors that control trend in long-term sequestration? For these questions, we made some assumptions. And the first one, since the climate was relatively stable during the Holocene, the intensification of human activity could be the main cause of increased carbon storage in lake from 4,000 BP. The second one was the meta-analysis could increase our knowledge of the spatial and temporal variation of carbon sequestration, which still does not exist at the moment for the Holocene. And the third assumption was the control factors differ from site to site, but we may have one or more common control factor regionally or globally. The methodology part of this study was based on an approach of paleolimnology, a meta-analysis, and of course, bibliographic research. At first, we made a research in specialized journals, the Holocene, but we got only 2 publications between 2006 and 2018. After that, we turned to the scientific platform Web of Science, which allows us to expand our research and allows research with a keyword. So we choose our selection criteria, age minimum and the maximum. The minimum age was the most recent, and the maximum age was 28,000 BP. And the keyword of our research were lakes, chlorophyll, carbon, Holocene, sediment, pigment, and either loss of ignition, because we didn't have enough sites with carbon. So we got 119 items for our research. In this 119 item, we got only 57 items with our selection criteria, and between these 15 we have 16 publications with chlorophyll A and carbon, 4 publications with chlorophyll A, and 43 publications with carbon or LOE. Once we did this, we processed to collect data directly from the publication, from deep age model, and from the variable curves of chlorophyll and carbon by digitalization. As you can see here, we made a digitalization of this curve to obtain the value of age and depth. And the second was to extract data from curves of carbon or chlorophyll. And we have an example to illustrate that. We took a screenshot of original data from the publication, for example, here, chlorophyll, and we made a digitalization. After that, we made a resampling and interpolation with RStudio. And finally, we got our 15 years interval and we got our data. So we did this with the chlorophyll curves and carbon curves, and we did this for all 15 sites. Once we have our data, so we made an extraction of climate and land cover variables. For example, for air temperature and maximum precipitation data, we extract data from ACAM6 for the last 8,000 years. And for land cover variables, we made an extraction of 6 variables for last 12,000 years from the EID database. After that, we made an interpolation with our 15 sites using the geographical coordinate of our lakes. And we got our big data. So the third part was the data analysis. Before starting data analysis, we made an undersampling for the period of study, which is between 400 BP and 8,000 BP, Holocene. So after this undersampling, we got 43 sites for buried organic carbons and 15 sites with land cover data and buried organic carbons, and 12 sites with buried organic carbons and chlorophyll. The results. So we made 2 statistical tests. The first one was the Menkendahl test. We used the Menkendahl test to reconstruct the trajectory of buried organic carbons over the Holocene. And we calculate the tau value, and the tau value, when the tau value is positive, so that explains we have a monotonic increase in our sites. And when the tau value is negative, that explains that we have a monotonic decrease in our sites. So the result was, for 43 sites, the red one represents decrease in buried organic carbons, and the green one represents an increase in buried carbon. And you see that we have as many sites increasing as sites decreasing. After that, we use the general additive models GAM for our 15 sites. Our 15 sites are represented in the map here. And we took buried organic carbons as a response variable, and we took the climate variables and land cover variables as an explanatory variables. So, and we made an extraction of p-values, and this box plot represents all the p-values of all variables during the Holocene. The result of this test shows that the density of population and pasture are the 2 most significant variables with our response variable, buried organic carbons, because they represent p-values under 0.05. And to show this effect of the effect of these variables on our buried organic carbons, we draw the prediction curves for temperature and pasture, and we draw the TOC trend. And here we took 2 examples. I took an example for site represent an increase in buried organic carbon, and I took another example for site represent a decreasing. For this site, we see that temperature is relatively stable during the Holocene, and we don't have an effect on our response variables. But if we take pasture, we see that from 8,000 BP and 4,000 BP, the pasture contributes negatively with our buried organic carbons, and from 4,000 BP, we see that pasture contribute positively with our buried organic carbon, and that is proved in our the third curve that represents the TOC trend, the buried organic carbon trend. The second example was the site representing a decreasing, and we see that temperature is relatively stable always, but for Pasteur, we see that for, between 8,000 BP and 4,000 BP, we have the Pasteur contribute positively with our buried organic carbon, but from 4,000 BP, it contributes negatively with our organic carbon. And that's why we see in TOC trend in the third curve, we have a decrease in buried organic carbon from 4,000 BP. So to obtain our synthetic curve of human effect, we summed the normalized values of pasture and cropland for curve production for 15 sites, and we obtain this. The first curve represents the sum of normalized value of temperature of prediction curves, and we see that the temperature is always stable during the Holocene. But if we take the second curve, we see that from 4,000 BP, we have an increase, which is accompanied by an increase in trends of buried organic carbon. And that could be explained by deforestation and land conversion, and also by can be explained by water input of alloctonous organic matter used by fertilizers used in agriculture. This is what has been shown in a previous study, that an increase in global rate of sediment transfer to lake is increasing from 4,000 BP, and that could be explained by soil erosion and land conversion. So the factor regulating the rate of carbon burial during the Holocene, we could say that the climate control this carbon sequestration between 10,000 BP and 6,000 BP, and from 4,000 BP, the agriculture and the human pressure that control the carbon sequestration. So as a conclusion, the first conclusion was to confirm our assumption made at first, is the first human trace for the buried organic carbon trace was detected from 4,000 BP, and we couldn't identify a special heterogeneity in buried organic strands, because we need more for more sites and for more studies, because we don't have enough studies. And the limit of this study, which is we didn't have enough study in America to generalize more our studies, and we didn't have sites in Africa. We didn't have any sites in Africa, and also the data collected may be over or underestimated. Thank you very much for your attention.
Thank you, Mohammed. That was really interesting. I have to say, this is a subject dear to my heart, and that really was excellent.
Thank you so much.
Do we have any questions? I think we have a few minutes if there are any.
Maybe I've got just one remark. This is Philippe speaking. So Mohammed did that work, and I think the regional and global ambition of the group of the pages, which is very good news. I think it's a very promising initiative to try both to fill the gap in the missing data, but also to identify part of the world where we have definitely a need for new acquisition of the data. So this is the kind of map that Mohammed showed us just previously, highlight quite well, I think, this point. Okay, so I think it's a very interesting, this kind of prospect for the group. Just a few words about Mohammed. Don't hesitate to contact him if you are looking for a talented and motivated student, as he is looking for a PhD. Thank you.
Thank you. Right.
I would have a question.
Yeah, please.
So thanks very much for this very interesting talk. I was wondering, to predict what is causing changes in carbon burial, you rely a lot on large-scale models and large-scale interpolation, so on climate models and on land use, large-scale land use interpolation. So do you think your results would differ, or how representative are these large-scale models for the local changes at your lakes? Do you think you could get a better result if you would have more local reconstructions of land use or local reconstructions of climate, or do you think, this wouldn't matter much?
Yes, for local land use, if we have more data, yes, I could have a very better results, because in 15.7 sites, I have only, in 15.7 sites, I have only, 15 sites with land cover data and climate. So I didn't have much, data with land cover and climate. So,
but Olivier, I completely subscribed to what you said. I think if you definitely, if you have the general circulation model for the climate reconstruction, go for it. But if you have some local reconstruction, especially based on the paleological archives, then you have to maybe go for an hybrid investigation using both the global data for the sites you have no access to the data, but if you have some empirical data, definitely go always for the empirical data.
Okay, thank you.